Water is the quintessential compound of nature. It plays an important role in a host of physical, chemical, and biological processes. At the same time, its quantity and quality, including its spatial and temporal distribution, pointedly touch all instances of human endeavor. The study of water continues to engage professionals in a variety of fields, including engineering, physics, chemistry, biology, geology, geography, sociology, and the law, to name some of the most important. Accordingly, it is an absolute necessity for learned professionals to understand water and its properties so that its stewardship and management may be accomplished in a rational way. The structure of the water molecule appears simple enough, but a complete characterization continues to defy scientists. A systematic study of water, in molecular form and in the aggregate, is much needed to throw additional light onto its capabilities and uses, and to understand why it is the chemical compound chosen by nature to condition and sustain life. Salient properties of water are the following: its capacity for ambient temperature regulation, its floatability in solid state, ice, its surface tension and capillarity properties, its marked solvent property, and its active relation with proton and electron chemistry. Here we endeavored to explore the properties of water with the objective of improving its management. The French chemist Antoine Lavoisier discovered that water is composed of two elements, oxygen and hydrogen. He recognized the name oxygen in 1778 and hydrogen in 1783. He gave hydrogen its name to mean generator of water. In 1804, another French chemist, Joseph Gay-Lussac, together with the German naturalist Alexander von Humboldt, showed that the water molecule consists of two atoms of hydrogen for each atom of oxygen to form the ubiquitous chemical formula H2O. The atoms of water are held together by sharing their electrons, the negatively charged subatomic particles that surround the positively charged nucleus. The nucleus of each atom of hydrogen, the smallest element in nature, contains one proton and one neutron, and it is orbited by one electron in a single layer that can admit a maximum of two. Thus, an atom of hydrogen can take one more electron in its single layer, which participates in the sharing of electrons with another hydrogen atom to form the hydrogen molecule, H2. An atom of oxygen has 8 protons and 8 neutrons in its nucleus, and 8 electrons orbiting it, 2 of which are located in a full inner layer and the other 6 in an incomplete outer layer, which can take up to 8 electrons. Thus, an atom of oxygen can take 2 more electrons in its outer layer, which participates in the sharing of electrons with another oxygen atom to form the oxygen molecule, O2. The pairs of shared electrons form covalent bonds, which provide the strongest attraction between atoms, constituting very stable molecules. To form a water molecule, H2O, one oxygen atom joins 2 hydrogen atoms, proceeding to share their electrons. Each one of the 2 hydrogen atoms shares its lone electron with the oxygen atom in its outer layer to fill in the 2 empty spaces, thus completing the layer to 8 electrons, while forming 2 covalent bonds. In this way, each hydrogen atom is full with 2 electrons in its single layer, and each oxygen atom is full with 8 electrons in its outer layer. The two strong covalent bonds keep the molecule together. A molecule of water has two pairs of shared electrons, that is, two simple covalent bonds. Note that the angle between the OH bonds is not 180 degrees or 90 degrees. It should be the case if the spatial distribution were planar, that is, two-dimensional. Rather, the water molecule has a three-dimensional structure, with its components arranged following a tetrahedral molecular geometry. If the tetrahedron were a regular one, the angle between the bonds would be 109.5 degrees. However, the tetrahedron of the water molecule is not regular. The oxygen atom occupies the center of the tetrahedron, and the two hydrogen atoms occupy each of two vertices, with the remaining two vertices housing the two pairs of oxygen electrons that are not part of the covalent bonds, constituting two electron clouds. This three-dimensional configuration results in a slightly irregular tetrahedron with an angle of 104.5 degrees between the two covalent bonds linking the oxygen atom and the two hydrogen atoms. The range in which water is in liquid state is ideal for the various life forms that are present on Earth. However, when it is compared with similar compounds, water should boil at a temperature lower than minus 59 degrees Celsius, not at 100 degrees Celsius. This table contains the values of molar mass and boiling point for several compounds labeled H2X, where X stands for elements located in the same column as oxygen in the periodic table of the elements. The molar mass M in grams per mole is defined as the mass in grams of a given substance divided by its amount in moles. Since water has the lowest molar mass among these compounds, the expectation is that it would have the lowest boiling point, not the highest. The apparent anomaly can be explained by the bond between water molecules, or hydrogen bond. In a water molecule, the oxygen nucleus with 8 positive charges attracts electrons better than the hydrogen nucleus with 1 positive charge. Hence, the oxygen atom is partially negatively charged, and the hydrogen atom is partially positively charged. The hydrogen atoms are not only strongly attached to the oxygen atoms by covalent bonds, but also weakly attracted to other nearby oxygen atoms by hydrogen bonds. Each water molecule can donate up to 2 hydrogens and accept other 2 in a tetrahedral structure. The hydrogen bond is a weak bond with a very short lifetime. The broken hydrogen bond, however, often simply reforms, being broken for very short periods of time, less than 100 femtoseconds. In solid state, that is ice, all water molecules participate in 4 hydrogen bonds, 2 as donor and 2 as acceptor, and are held in relatively static state. In liquid state, some of the weaker hydrogen bonds break to allow the molecules to move around. This continues to happen with an increase in temperature up to the boiling point. The large amount of energy required to break these bonds must be supplied during the melting and boiling processes. The molecules of hydrogen telluride, hydrogen selenide, and hydrogen sulfide exhibit dipole-to-dipole intermolecular forces, which are attractive forces between the positive end of one polar molecule and the negative end of another, forming a bond which is weaker than a hydrogen bond. In summary, a hydrogen bond increases the intermolecular cohesion, which prevents water molecules from being easily released from the water surface. Consequently, the vapor pressure is reduced. As the boiling point cannot occur Until the vapor pressure equals the external pressure, a higher temperature is required. The boiling point of water is a function of ambient pressure. For instance, at the peak of Mount Everest, at an elevation of 8,848 meters, water boils at 70 degrees Celsius, while in the deep sea it remains liquid above 300 degrees Celsius. To understand this behavior, we must examine the relation between temperature and pressure. The mobility of a water molecule increases with temperature and decreases with pressure. At high altitude, the atmospheric pressure is lower, resulting in more mobility. For this reason, the temperature necessary to reach the boiling point is lower. This figure shows a phase diagram illustrating the preferred physical states of water at different ranges of temperature and pressure. At TP, or triple point, the three stable phases, solid, liquid, and gaseous, may coexist at equilibrium. On the other hand, at CP, or critical point, the properties of liquid and gaseous phases become indistinguishable from each other. Under sufficiently high temperature and pressure, liquid water is hot enough and gaseous water is under enough pressure for their densities to be equal. The change of water from liquid to gaseous phase occurs with energy absorption. Two measures describe the change. One, the specific heat capacity, and two, the heat of vaporization. The specific heat capacity is the amount of energy per unit mass of water required to raise its temperature by 1 degree Celsius. The heat of vaporization is the amount of energy required to convert 1 gram of water from liquid to gaseous state at constant temperature. Water has the highest specific heat capacity of all liquids except ammonia, because a great amount of energy is required to break the hydrogen bonds. Since the energy absorbed in this process is not available to increase the water's kinetic energy, it takes a greater quantity of heat to raise the temperature of water. In addition, it takes a great amount of energy to change water from liquid to gaseous state because of the energy required to break the hydrogen bonds. Consequently, water has the highest heat of vaporization of any liquid and hence a very low volatility. This property of water is important for regional climate regulation, explaining the marked difference between hyperoceanic and inland continental climates. For instance, the state of North Dakota, with an inland continental climate, is subject to more temperature variability between winter and summer than the entire U.S. average, which is influenced by hyperoceanic climates. The density of water varies with temperature within a very narrow range. Typically, liquid substances shrink with a decrease in temperature, thereby increasing their densities. However, liquid water presents a unique behavior, contracting with temperature reduction until the temperature reaches 4 degrees Celsius. At this point, water reaches the maximum density of 1 gram per cubic centimeter, after which it begins to expand, decreasing its density and allowing its solid form, that is, ice, to float. The higher density at 4 degrees Celsius may be explained by analyzing ice structure. The H2O molecules form an hexagonal grid of tetrahedral geometry. This configuration assures that ice molecules are less compacted than water molecules, occupying a greater volume. Thus, the cooling to 4 degrees Celsius results in the expansion of the space between water molecules, decreasing its density. In nature, the change in water density with temperature at or near 4 degrees Celsius is responsible for the thermal stratification of the water column. In the absence of mixing, At 4 degrees Celsius, the top layer will cool to the freezing point and ice will form on the surface. This ice layer will block the exchange of energy between the cold air above and the warm water below. Therefore, the ambient cooling continues, but with no drop of temperature in the water column below. The formation of an ice layer on the surface of the water body discourages the freezing of the water column. Therefore, it makes possible the survival of aquatic plants and animals in lakes and seas. Due to high cohesive forces, water molecules at the surface are more attracted to the molecules within the liquid than they are to molecules of air outside of it, producing surface tension at the gaseous liquid interface. In contrast, molecules of water inside the liquid are equally attracted in all directions. This property makes it more difficult to move an object through the surface than to move it when it is completely submerged. That is why insects, which are heavier than water, can float and slide on a water surface. The movement of water up or down capillary tubes is due to surface tension. Capillary action occurs when the adhesion of water molecules to the walls is stronger than the cohesive forces between the liquid molecules. The meniscus is the curved liquid gaseous surface interface. It is concave when the liquid molecules are strongly attracted due to adhesion to the walls of the container, as in the case of water. Conversely, the meniscus is convex when the liquid molecules have a stronger attraction to each other due to cohesion than to the wall of the container, as with mercury. Capillary action makes it possible for plants to thrive. Capillarity allows subsurface water to move up into the root zone, but only up to a small distance, after which it cannot overcome gravity. Due to strong cohesion forces, the water molecules that evaporate on the leaf surface attract others in the neighborhood, helping the water to get up the plant, eventually reaching all branches. Within the soil profile, the capillary height is 2 to 5 centimeters in coarse sand, increasing as the soil particle diameter decreases, reaching more than 3 to 4 meters in some cases. The water molecule has the property of polarity, featuring a relatively large dipole moment. The dipole moment arises because oxygen is more negatively charged than hydrogen. Thus, oxygen pulls in the shared electrons, increasing the electron density around itself. The dipole moment of water is mu equal 1.85 d, where d stands for dBi, with d equal to 10 to the minus 18 stat coulomb centimeter. The polarity of water is important for many of its properties, including the ability to dissolve solutes, melting and boiling points, specific heat, surface tension, and general reactivity. Water can dissolve almost anything, and therefore it is regarded as the universal solvent. Water's large dipole moment is associated with its relatively high dielectric constant. Coulomb's law, named after the French physicist Charles de Coulomb, states that the force F between two charged particles is inversely proportional to the medium's dielectric constant K. That is, the greater the K, the lesser the force F. In a vacuum, K is equal to 1. For water, K is equal to 78.5. This large value of K, derived from the water molecule's polarity, makes it possible for the substances formed by the association of two charged components to disassociate readily in water, and that all polar substances see their attraction and repulsion forces diminished. Moreover, the presence of dissolved ions in water results in a marked increase in its electrical conductivity. Otherwise, water would behave essentially as a non-conductive medium because of its patent lack of native ions in its pure state. In salt water, electricity is conducted by ions. Sodium ions absorb electrons from the negative terminal, passing them to chlorine ions and then to the positive terminal, forming a bridge which conducts electrical current. Distilled water has a very low electrical conductivity of 0.0000055 decisiemens per meter. Potable water is around 0.1 to 0.5 decisiemens per meter, and seawater about 44 decisiemens per meter. Therefore, the greater the salinity of the water, that is, the greater the concentration of ions in the solution, the greater its electrical conductivity. Life, which is based on carbon chemistry, requires a liquid medium to develop effectively. Water in its liquid state is the best medium for that chemistry. Water is required for the dissolution of chemical compounds that sustain life and for the transport of nutrients and wastes. These compounds include salts, sugars, acids, bases, and gases such as oxygen and carbon dioxide. In addition, water associates itself to the polar regions of organic compounds such as lipids, proteins, and nucleic acids. Often these compounds form hydrogen bonds with water, which are weak attractions between a proton in one molecule and an electronegative atom in the other. The energy driving biological processes is generally due to gradients of proton concentration in an aqueous medium on both sides of a membrane. A proton of hydrogen is an atom of hydrogen which is missing its electron. The water molecule has a weak capacity to spontaneously separate into two distinct ionic components. One, the hydronium ion, or positively charged cation, H3O positive, which is a water molecule with an attached hydrogen proton. And two, the hydroxide ion, or negatively charged anion, OH minus, which is a water molecule with a hydrogen proton missing in a reversible formula. In pure water, the concentrations of hydronium and hydroxide ions are very small and identical, each being 10 to the minus 7 moles per liter at 25 degrees Celsius. The concept of pH for percentage of hydronium is used to characterize the purity of water. The pH is the negative of the exponent of the concentration of hydronium ions. Thus, a pH equals 7 refers to pure or neutral water. For a higher hydronium concentration, say 10 to the minus 6 moles per liter, the water solution would be acid. Conversely, for a lower hydronium concentration, say 10 to the minus 8 moles per liter, the water molecule would be basic. The pH of water decreases sharply in a solution containing large quantities of a strong acid such as hydrochloric acid. The molecules of hydrochloric acid readily donate their protons to increase the concentration of hydronium ions, that is, decrease the pH of the solution. Likewise, the pH of water increases sharply in a solution containing large quantities of a strong base such as sodium hydroxide. The molecules of sodium hydroxide readily accept protons to decrease the concentration of hydronium ions, that is, increase the pH of the solution. All organisms have a range of pH in which their body fluids remain healthy. Values of pH too high or too low may cause damage to cells. Normal values generally tend to be close to neutral, that is pH 7. This figure shows typical aqueous solutions in a pH scale. The concentration of electrons in an aqueous medium is useful in characterizing the various stages of the oxidation reduction process. For this purpose, the concept of redox potential or oxidation reduction potential, ORP, is used. Its complementarity to pH in conditioning biochemical processes is indeed remarkable. It is also referred to as E or E sub H, or alternatively expressed as a corresponding PE scale. Redox potential is a measure of the affinity of a substance to lose or gain electrons and thereby to be oxidized or reduced, respectively. The standard is hydrogen with zero redox potential, or E equals 0 millivolts. In well-oxidized water with dissolved oxygen concentrations above 1 milligram per liter, the redox potential is highly positive, about 300 to 500 millivolts, and can reach up to 800 millivolts under conditions of optimum oxidation. In reduced environments where dissolved oxygen is lacking, the redox potential is small positive, approximately 100 millivolts, and may even reach negative values. Extremely reduced environments may feature a redox potential as low as minus 400 millivolts. A positive value of redox potential indicates that a substance is an oxidizing agent. The higher the reading, the more oxidizing it is. As such, a substance with a reading of 400 millivolts is 4 times more oxidizing than a substance with a reading of 100 millivolts. Conversely, a negative reading indicates that a substance is a reducing agent. The lower the reading, the more reducing it is. Thus, a substance with a reading of minus 400 millivolts is 4 times more reducing than a substance with a reading of minus 100 millivolts. Most types of water, including tap water and bottled water, are oxidizing agents as their value of redox potential is positive. Alkaline ionized water is a reducing agent as it has a negative value of redox potential and it is able to donate extra electrons to neutralize the harmful effects of free radicals on the organism. However, most other types of water are oxidizing agents as the redox potential is positive. In wetland ecosystems, the redox potential conditions the time sequence of various types of oxidation reduction reactions in newly flooded organic substrate, ranging from oxygen reduction, a highly positive redox potential, E equal 800 millivolts, to methanogenesis at the very low negative values, E equal to minus 400 millivolts. This figure shows the decrease with time of the relative concentration of electrons in seasonally flooded soils. The physical, chemical, and biological properties of water are reviewed with the aim to understand the diverse role of the water molecule in conditioning and supporting life. The singular properties of water make it well suited for the development of carbon chemistry, helping sustain life in all of its myriad forms. Therefore, the properties of water span physics, chemistry, and biology, almost as if nature had intended for the 3 fields to coalesce into one.